Welcome to section 2.3 of the text Discrete Mathematics and its Applications, Math 160, Discrete Methods, here at Anderson University. Functions. This is Dr. Gilbert Eyabi. Firstly, let's go ahead and look at the lesson objectives for today. We would look at the definition of a function, domain, codomain, image, pre-image. What does it mean for a function to be injective, surjective, bijective? Then we shall look at the concept of an inverse function, the composition of functions, graphing functions, floor, ceiling, and factorial functions. And if we have time, we may talk about partial functions. That's optional, and we would most likely not do that in this lecture. Okay, functions. What is a function? Let A and B be non-empty sets. If a set is empty, there is not very much you can do with that set. So the very first assumption is that the set A is not empty and the set B is non-empty. So if that is assumed, we would say that a function f from A to B, denoted by this, is an assignment of each element of A to exactly one element of B, i.e., for every element in A, exactly one element from B that the element A is mapped onto. There are a couple of things I need you to see here. Number one, every element in A is mapped onto some element. Okay, so if there is an element in A that is not mapped onto B, some element in B, then that would not be a function. So every element in A has to be used up. And number two, an element in A can be mapped to exactly one element in B. An element cannot be mapped to more than one element in B. So think of the birthday function. And A is the set that contains people, and B would be their birthdays. So John cannot be mapped to January 1st and then mapped to September 11th at the same time. That means he has two birthdays. That's not possible. Okay? But John can be mapped to January 1st, Mary to January 1st, Josephine to January 1st, Peter to January 1st, Edmond to January 1st, Susan to January 1st, and so on and so forth. Okay? But every element in A has to be used up. But if it is from A, it has to be mapped to exactly one element in B. Okay, if that happens, we write f of A equals B. That means f maps A to B, and B is the unique element of B that is assigned to the element A of A. So let's look at this little example. Ignore what I have here added in red, students and grades. Okay, so you can see Rodriguez got an A, and Sandeep got a B, and Williams got a B, and Scott got an A. That is a function. All the elements from the set A have been used up. And wait a minute, I have some elements here from B that were not considered, like C, D, F. Is that a problem? No. Right here, this set constitute what is known as our domain, and over here this set constitute what is known as our codomain. But A and B would be our range. So the range is going to be a subset of, and we would explain that later as we move on with our lecture. Now, I've added this red right here. So under Williams, I have an arrow that goes to B and an arrow that goes to D. That makes it not a function, because that means Williams got a B in the class and he also got a D in the class. That's a problem. That wouldn't make it a function. Now, if you ignore that, and then maybe you add another person here, John Peters. John Peters is not mapped to any grade. That also will not make it a function. Sometimes we call functions mappings or transformations. When you take Math 215, linear algebra, we will talk some more about linear transformations. Okay, let's continue our discussion on functions. A function f from A to B can also be defined as the Cartesian product of A and B, which is a relation, and we will talk more about relations further in this class. But right now, all I can say is that A is said to be related to B if and only if some criteria are satisfied. And I'm not going to go beyond that right now because we have not yet looked at relations. Okay, now let me introduce the concept of domain and codomain in detail. If f is a function from A to B, we say that f maps A to B, or f is a mapping from A to B. So right here, that is my A, that is my B, and A is my domain, and B is my codomain. A particular element from A is mapped onto an element in B called B, but B is actually written as f of A. Okay, so whenever A is mapped onto B, that simply means B is f of A. A has been assigned to B by f. Okay, now f of A right here would be the set of all f of little a's, where A is an element in A. We will look at some examples. And this is a subset of the codomain B. Again, just like we mentioned up here, f of A would simply be the set with elements AB, which is a subset of the codomain A, B, C, D, F. Okay, and that is our range. Or we could also say that is the image of the domain, the image of the set A. Whereas my little a right here would be the image of Rodriguez. Let's go and look at that a little bit more. A is called the domain of F. B is called the codomain of F. So if f of A equals B, which means A has been assigned to B by F, then B is called the image of A under F, and A is called the pre-image of B. But we can also talk of the image of the entire set A, that is the range of F. So the range of F is the set of all images of points in A under F, and we denote it by f of A. So f of A is the set of all images, all f of A, such that A is an element in A. Now, before we proceed, it is important to note when two functions are equal, okay? And we will do that in almost every class. In linear algebra, we will discuss what it means for two matrices to be equal, what it means for two vectors to be equal. Well, what does it mean for two functions to be equal? Two functions are equal if and only if, number one, they have the same domain and codomains, and number two, they agree at every point in their domain, i.e., f of x equals g of x for every x in A. So two functions are equal if and only if they have the same domain and codomain and they agree at every point on their domain. Otherwise, the two functions are not equal. Okay, now let's talk about representation of functions. We could represent functions with explicit statement of the assignment, students and grades, example, the one we just saw, but we would not do that very often. We would use a formula. For example, f of x equals x plus 1, and we would state what the domain is, of course. If the domain is the set of all integers, that means if I take f of 1, that gives me 2. F of 3, that gives me 4. F of 5, that gives me 6, and so on and so forth. It's almost impossible to explicitly define the function using statements like we did with the students and their grades. That's not going to happen because if I have 10,000 students and different grades, trying to explicitly in the form of a statement to put that down, it's a little bit difficult. If both sets are infinite, it's impossible to list down the elements of the set, so we just have to go with a formula. Programmers also use computer programs. For example, a Java program that when given an integer n produces the nth Fibonacci number. Okay, so that's going to be a function. But we would mostly be interested in a function defined as a formula in this class. Let's look at an example. So that is my set A, That is my set B. So that's the domain and that's the codomain. First of all, is this a function? Well, all the elements in A have been used up and were assigned to different elements in B, so that's good. And I do not see an element assigned to more than one element in B, so that appears to be a function. The range is just YZ. So now we can answer a couple of questions. So what is f of A? A is mapped onto Z. What is the image of D? What's the domain of F? What is the codomain of F? What is the pre-image of Y? And what is f of A? There's these two elements, and so on and so forth. Okay, it's pretty easy and straightforward if I define my functions with explicit statements like this. But I expect you to be able to get this done even when it is defined using a formula. Okay, here's another example. Question on functions and sets. Let f be a function from A to B. Again, A and B are not empty. Now, let S be a subset of A. We can talk about the image of S. So if f is a mapping from A to B and S is a subset of A, then f of S is the set of all elements Y in B such that Y equals f of X, where X is from S, you see. So instead of dealing with the entire domain, I'm interested in just a subset of the domain called S. And that is nothing but a set of all f of X, where X is an element in S. So for example, if S is the set ABC, then ABC is a subset of A. And f of S would simply be the set of all f of X such that X is from S, and that would be ABC is mapped to Y and Z, so that would be just Y and Z. You can do the same if S were the set CD, and so on and so forth. Okay, injections. What does it mean for a function f to be one-to-one or to be injective? It has very little to do with this in the hospital. Okay, now a function f is said to be one-to-one or to be injective if whenever f of A equals f of B, we have that A equals B. And of course, it's an if and only if statements, which means when f of A equals f of B implies that A equals B, we would say that f is one-to-one, and if f is one-to-one, then this holds. What I'm really interested in is what happens when you're dealing with proofs. Okay, in proofs, if you are required to prove that f is one-to-one, then this is how you proceed. Proof. Suppose f of X equals f of Y, where X and Y are elements from A. You have to proceed to show that X equals Y. If that happens, you conclude that the function is one-to-one. For example, let f be the function with domain, the set of real numbers, and codomain, the set of real numbers, defined by f of X equals 3x plus 2. Is f one-to-one? Proof. Suppose f of X equals f of Y. What does that mean? Well, that means 3x plus 2 equals 3y plus 2. Recall that this x here is a dummy variable. I could have said suppose f of A equals f of B and just replace x with A and B. Again, adding the additive inverse of 2 on both sides. In elementary school, we say subtract 2 from both sides, but actually what we're doing is we're adding the additive inverse on both sides, which is negative 2, where we end up with 3x equals 3y. And we multiply both sides from the left with the multiplicative inverse of 3. In elementary school, we say we divide both sides by 3. It's okay, I can live with that. We end up with x equals y, and therefore f is an injection. And you can see that here. A is mapped to Z, B is mapped to Y, C is mapped to X, D is mapped to W. So they're all mapped to one element. No two of them is mapped to the same element. So that's a one-to-one mapping. Now, that does not mean that all the elements in B are used up. It just means that no two elements from A are mapped to the same element in B. Now, what happens if all the elements in B are also used up? That becomes a very exciting category of functions, and they are known as surjective functions. And watch very carefully how I define a surjective function. A function f from a to b is said to be onto or surjective if and only if for every element b in b, that is number one, there exists an element a in a such that f of a equals b. Now, see the way I've numbered them? That is kind of how the proof strategy goes. So we start first by picking an element b in b, that is number one. Suppose actually f of a equals f of b, number two. Then we find an a, number three, and the a has to be in a, number four. If that happens, then we say it is surjective. Here is an example. F from z to r, set of integers to the set of real numbers, defined by f of x equals 3x plus 2 is f onto. Watch, the domain is the set of integers. And I've done this intentionally because I want to show you that the domain matters a lot when you're determining whether a function is onto or not. Proof. Let B be an element in R. So I pick an element from the codomain. Again, that is my number one. Okay. F of A equals B if and only if. You see, I'm not saying that there exists an A in A such that f of A equals B. Now I'm saying that that would happen if and only if. So I'm not saying that it has already happened. But if it were to happen, so f of A equals B if and only if 3a plus 2 equals B. Okay, remember that's a dummy variable. So f of A will be 3a plus 2. And that will happen if and only if 3a equals b minus 2. We can say you subtract 2 on both sides, or we just simply say you add the additive inverse of 2 on both sides, which is negative 2. And then we end up with a equals b minus 2 divided by 3. So number one, we pick a b from the codomain. Number two, f of a equals f of b if and only if. Number three, we solve for a. Are we done yet? No. We have to verify that the a we have is from the domain. In this particular case, our domain is a sort of integers. So if I pick my b to be the number 3, then a will be 1/3, which is not an integer. So f is not onto. But observe that if I change the domain and my domain becomes the set of real numbers, this should be dom f, not dom a. So if I change my domain and the domain of my function f is the set of real numbers, then my a equals b minus 2 divided by 3 is going to be in R, in which case f becomes onto. Okay, so the domain matters a lot. It can determine whether a function is onto or not. Again, change that to dom f, not dom a. So what happens if a function is both one-to-one and onto? If that is the case, we say the function is bijective, i.e., we just arrived at a bijection. And this is the kind of picture we have. All the elements in A are used up. All the elements in B are used up. And because all the elements in B are used up, we can talk of a reverse function. We can go the reverse direction. So f goes from A to B, and f inverse goes from B back to A. For example, if I change my domain above as a function f from R to R, set of real numbers, defined by f of x equals 3x plus 2, then f is going to be both one-to-one and onto. And f inverse, believe it or not, recall that when we solved for a, we got our a to be b minus 2 divided by 3. Well, believe it or not, that's what we got. F inverse of x is simply going to be what your a was. And so f inverse of x is x minus 2 divided by 3, where the b is replaced by x. I have x minus 2 divided by 3. And that should be a 2. I'm not sure why it's an a. So just ignore all of that right there. Okay, so check out the function f from z to r, defined by f of x equals x minus 5. Is this a bijection? Again, recall that the domain is a sort of integers. But if the coefficient of x is 1 instead of 3, as we have it here, would that make it a bijection? Okay, go ahead and play with that, and let's see what you get. Okay, very good. Okay, as a summary, here is how we show that a function is one-to-one or onto. Number one, to show that the function is injective or one-to-one, we suppose that f of x equals f of y, and then show that x equals y. Okay, that's just good enough. And to show that f is not injective, we would show that there exist two elements x and y in A such that x is different from y, but f of x equals f of y. For example, f of x equals x squared. Pick two elements from the domain A. Let's say A is a set of real numbers. So take -2 and 2. F of -2 is 4. F of 2 is 4. So f of x equals f of y, but 2 is different from -2, so it is not injective. To show that f is surjective or onto, we pick an arbitrary element y in B, and then we find an element A that has to be in A such that f of A equals B. And to show that f is not injective, we find a particular element y in B such that that relationship does not hold. That is what we did here. So to show that it was not surjective, we picked a particular element from the codomain. In this case, we picked a 3. And we got A to be 1/3, which is not an integer. So in other words, for the element 3, there is no A in the domain such that f of A equals B. So that is how you prove that a function is not surjective. Okay, let's take one big example. Let f be the function with domain, the set of real numbers, except the points -1/5 and 3 divided by 5, and the codomain is the set of real numbers. F is defined by 3x plus 2 divided by 5x plus 1. We're going to verify whether f is 1-to-1, whether it's onto. If both, then that means it's bijective, and then we're going to find the inverse if that is the case. So let's start by verifying whether f is 1-to-1. Suppose f of x equals f of y, where both x and y are in the domain of f, right here. We want to verify whether x equals y. But f of x equals f of y would mean that this expression equals this expression. If I cross multiply and I distribute, just do some little arithmetic and mathematics put together, slight touch of algebra, I end up with x equals y, so f is 1-to-1. Now, is f onto? Proof. Let B be an element from the codomain R, the set of real numbers. My goal is to find a number A from the domain such that B equals f of A. But like we did before, B would be equal to f of A if and only if B equals 3a plus 2 divided by 5a plus 1. Again, I cross multiply and solve for A, and I end up with A equals 2 minus B divided by 5b minus 2. And I have to ask myself if this element comfortably sits in the domain. The only time this element would not sit in the domain would be when the denominator vanishes, and that happens when B is 3 divided by 5. Fortunately for us, 3 divided by 5 is not part of the domain, so yes, the function is onto. So it is both 1-to-1 and onto, and that means it is bijective. If it is bijective, that means f inverse exists. And what is f inverse? F inverse, you simply go back to your A and replace your B with x. So your f inverse of x would simply be 2 minus x divided by 5x minus 3. So f is a mapping from the domain to the codomain, and f inverse is a mapping from the codomain back to the domain. And that brings us to the end of the analysis of our interesting function. Let's proceed. Showing that f is 1-to-1 or onto, we could use examples with finite sets, and where your A is just A, B, C, D, and your codomain is 1, 2, 3, and I define my function f as follows and ask you the question, is f onto? If I pick any element from my codomain, is there an element from the domain that is mapped onto it? Yes, you can verify that. Is this function here 1-to-1 and onto? We can verify that. And then the concept of inverse functions, which I already introduced. Again, that is my domain, that is my codomain. f maps from A to B and f inverse from B back to A. As long as f is a bijection, I can always define f inverse. Now observe that f inverse of y equals x if and only if f of x equals y. Well, basically it's like you hit both sides of this function with f. F composed with f inverse is just the identity, so that leaves you with y, and on the right hand side you have f of x. So this is not very big, and we would introduce this some more as we look at proofs involving functions. So here's what we're talking about when it comes to inverse functions. So that is f, and that is f inverse. Okay, here is an example. Let f be a function from A to B. Again, these are finite sets. I don't care very much for finite sets. You should be able to define a function on infinite sets and verify onto one-to-one existence of inverse and also find f inverse. But at the same time, it's okay to also be able to define f on finite sets and determine whether it's onto, whether it's one-to-one, and then find the inverse. Okay, and here is an example with all of that. Another example, which is probably what I prefer, let f be a function mapped from the set of integers to the set of integers, and f is defined by f of x equals x plus 1. Is f invertible? If so, what is its inverse? Number one, you can quickly verify that f is 1-to-1. Number two, you can verify that f is actually onto, because the coefficient of x here is 1. And so all you have to do is solve for your x as we did before, or say solve for a as we did before, and you arrive at f inverse of x to be x minus 1. If you want to call it f inverse of y, that's okay, but we can just leave it at x since x is like the standard dummy variable. So f inverse of x will just be x minus 1. Go ahead and verify this in detail. I leave the verification as a simple exercise for serious students. And example 3, define f from the set R to the set R, where R is the set of real numbers, by f of x equals x squared. Is f invertible? And if so, what is its inverse? Well, I think I gave this example already. If I take my x to be 2 and my y to be -2, then 2 is different from -2, but f of 2 is 4, f of -2 is 4, so f is not 1-to-1, and therefore we cannot even talk about the inverse of f. It's not invertible. Now, let's talk about composition of a function. If f is a mapping from B to C and G is a mapping from A to B, so observe that we're going from A to B, B to C. So I have it up here. I'm going from A to B, B to C. So G picks an element from A and takes it on to B. F picks the element from B and takes it on to C. So I can define a mapping from A directly to C known as the composition of F and G, known as F composed with G. So F composed with G is a mapping from A to C. And the most important part is that F composed with G of X equals F of G of X. So G feeds on X and F feeds on G of X. Okay, that's what I need you to remember. G feeds on X and F feeds on G of X, and X is from A. Now let's see how that works. So let's start with the element A. G takes the element A and produces G of A. F takes the element G of A and produces F of G of A. So you see, G feeds on A and F feeds on G of A. Look at this example. That is my set A, B, and that's my set C. So G takes A to Y and F takes Y to J. So F composed with G, A goes to J. So instead of all of these, I have one function known as the composition of F and G, and it takes an element from A straight to J. But internally, it passed it through Y and then to J. Okay, let's take another example. Define f of x as x squared and g of x as 2x plus 1. Assume A, B, and C all the domains and codomains are properly defined. So let's go ahead and compose f and g. So f composed with g of x equals f of g of x, and that equals f of, what is g of x? G of x is 2x plus 1. So you see, g feeds on x and g produces 2x plus 1. F feeds on 2x plus 1 and produces x squared, but the x there is going to be 2x plus 1. Okay, so g feeds on x and produces 2x plus 1. F takes on 2x plus 1 and produces 2x plus 1, all of that squared. Now, what happens if we define GOF, G composed with F? So G composed with F of X would be G of F of X. Again, knowing this definition is what is more important to me. So F feeds on X and produces X squared. So G of F of X equals G of X squared. And what does G do? G takes X squared and outputs 2X squared plus 1. Okay, so that is F composed with G, and this is G composed with F, composition of functions. And as we've done in this class, here's an example with finite sets and defined as follows. We have our G, we have our F, and we expect you to find the composition F composed with G. It's a straightforward example. So let G be the function from A, B, C, defined as G of A equals B, G of B equals C, G of C equals A, and F is the function on ABC, 2, 1, 2, 3. F of A is 3, F of B is 2, F of C is 1. So we can define F composed with G. So F composed with G of A will be F of G of A, but what is G of A? G of A is B. What is F of B? 2, and so on and so forth. Okay, again, these are examples with finite sets, which I don't want you to concentrate so much on. I need you to be able to look at infinite sets and generate a proof, because that is what abstract algebra is all about, and that is where I'm hoping to take you. Okay, so here we go. Let f and g be functions from the set of integers to the set of integers. Both sets, of course, are the same set of integers, and it's infinite. Defined by f of x is 2x plus 3, and g of x is 3x plus 2. Find the composition f composed with g and g composed with f. F composed with g is f of g of x. Again, this is the most important part. You need to write f composed with g as f of g of x. What does g do when g sees x? It outputs 3x plus 2. What does f do when it picks any element? It outputs 2 times that element plus 3. So if f picks on 3x plus 2, it outputs 2 times 3x plus 2 plus 3. Stick with the definition. Mathematicians swear by definition. If somebody tells you there is a mathematician swearing at the corner there somewhere, what he's simply doing is he's quoting definitions. Okay, we stand on definition. The definition of f is 2x plus 3. That means when f picks any element, it outputs 2 times that element plus 3. So f of John would be 2 John plus 3. F of Mary will be 2 Mary plus 3. F of 3x plus 2 will be 2 times 3x plus 2 plus 3. Okay, what about GOF? G composed with f of x, that will be g of f of x, which is g of, what does f do when it sees x? It outputs 2x plus 3. What does g do when it sees any element? It multiplies the element by 3 and then adds 2. So g of 2x plus 3 is 3 times 2x plus 3 plus 2, which is 6x plus 11. So just off the bat, f composed with g is not necessarily the same as g composed with f. In fact, they'll be different most of the time. Okay. Now let's look a little bit into graphs of functions. If I were to graph a function, all I need to do is produce ordered pairs. For every value of x, I get a corresponding value y. For example, I have negative 3, 9, negative 2, 4, negative 1, 1, 1, 1, 2, 4, 3, 9, 0, 0. And you can already tell that this is going to be the function f of x equals x squared. Okay. And f of n equals 2n plus 1. That is discrete because it's the set of integers to the set of integers. So you can see those values I have there. Now, here are some important functions that I have for you. They are known as the floor function and the ceiling function. The floor function is defined as follows, and it is simply the largest integer less than or equal to x. For example, the floor of 3.5 is 3. 3 is the largest integer less than or equal to 3.5. So the floor of 3 will be 3. The floor of 3.5 is 3. The floor of 3.7 is 3. The largest integer less than. The ceiling function, on the other hand, is the smallest integer greater than. So the smallest integer greater than 3.5 is 4. So the ceiling of 3.1 will be 4. The ceiling of 3.05 would be 4. And the ceiling of 4 would be 4. Okay. We will need this further in abstract algebra and also in your research. There are certain times you may want to restrict your output to integers, but there's a possibility that you could either get fractions or decimals. What do? You can use ceiling and floor functions depending on what kind of research you're doing, okay? And here are the graphs of our ceiling and our floor functions. And here are some computations or properties or characteristics involving floor and ceiling functions. And I'll just let you look at these for a few seconds. 1a, 1b, 1c, 1d, 2, 3a, 3b, 4a, 4b. We would probably see a couple of these in class as we look at a few problems. So this brings us to the end of our discussion on functions for now. Later on, we would want to ask ourselves, how do we prove or disprove that f of a intersection b equals f of a intersection f of b, or f of a union b equals f of a intersection f of b, or f inverse of a intersection b equals f inverse of a intersection f inverse of b, or f inverse of a union b equals f inverse of a union f inverse of b, using set inclusions. Those are some exciting proofs we would look at later concerning functions. But for now, Math 160 discrete methods, we would end at this point. Thank you and God bless you, and I'll see you in section 2.4. Bye-bye.